Hello students. In this particular video, we are going to see the basic digital circuits which are responsible for basic operations that are going to be performed by digital systems. In a digital system, there are few basic operations that has to be performed, irrespective of how complex the circuit is. These operations may be performed n number of times in any particular digital system, no matter whether it's small or large or complex or easy. Any type of digital circuit, if you consider, these are the operations that we have to perform. So in this video, I'm going to explain you about the operations that are going to be performed in any digital system. There are three basic operations that has to be performed. These basic operations are AND operation, OR operation, and NOT operation. These are the backbones of any digital systems. If you consider computers, mobiles, internet, anything which is based on digital system, it has to perform somewhere the operations like AND or NOT. These operations are responsible for changing the course of the program, making some valid decisions whenever required. That time, the operations that has to be helping the programmer are and or are not operations. If these operations are to be performed, these has to be performed n number of times, no matter how complex the circuit is. To perform these operations, we required specific circuits called as logic gates. These operations are designed in digital circuits, and those digital circuits are called as logic gates. The logic gates responsible for each basic operation that is going to be performed. So for performing AND operation, we required AND gate. To perform OR operation, we required OR gate, and to perform NOT operation, we required NOT logic gate. So we'll see all these basic operations. But first of all, let us see what are different types of logic gates that are available to you. There are few basic types of logic gates that are available. First one, we called it as a basic gates, which are going to perform some basic operations like AND, OR, and NOT operations. But depending upon the type of gate that you use, that is two or more gates that you use, there are derived gates. Derived gates are derived from using two or more basic gates simultaneously. So if you use the AND gate and OR gate together, it is going to create some kind of operation. If you use NOT gate and OR gate, if you use NOT gate and AND gate, these are the gates that are going to create a combination of gates. So therefore they are called as derived gates. In derived gates, there are special gates. The special gates are XOR and XNOR. And there are universal gates. The universal gates are NAND gate and NOR gate. So overall, in front of your screen, there are 7 gates, 3 basic gates AND, OR, and NOT, 2 special gates XOR and XNOR, and universal gates NAND and NOR. With the help of these gates, we will be able to understand the basic operations that has to be performed in any digital systems. First of all, let us see the basic gates. In basic gate, first operation that will be performed by AND gate is called as AND operation. This is a standard symbol that is used to represent the AND gate. In this symbol, you can see there are for that particular shape there are A, B, C up to N different inputs and one output. That means the AND gate has n number of inputs but only one output. So n number of inputs, that means more than two or more than two inputs may be possibly given to any AND gate, but the output will have only one output line, that is Y in this case. So therefore, its logical equation or Boolean equation, we called it as a Boolean equation also. Logical equation or Boolean equation is y is equal to a and b and c and dot 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 up to n. So therefore, if any two inputs, if you consider, are given to AND gate, the output will be the operation of AND between A and B. In this case, AND C and D dot 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 up to n. So symbolically, it is written down as A dot B dot C dot 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 up to n, where this dot represents a logic multiplication. This is completely different than the multiplication we have seen in algebra. In algebra multiplication, we have seen that decimal numbers 0 to 9 can be used to represent the multiplication between the two. So cross will be used to represent that multiplication. Here the logical multiplication is different than that particular. But overall, AND operation means nothing but a logical multiplication. So the truth table for two input AND gate is like this. You can see here the inputs are, since there are two inputs, so therefore the four combinations, unique combinations can be derived. You can see here 0, 0 are the two input signals that can be given to the NAND gate whose inputs are A and B. Then 0, 1, 1, 0 and 1, 1. Right? So these are the all possible inputs that can be given to any any AND gate. So therefore, when you consider output, then you can see output for this case, that is when inputs are 0, 0, then outputs in this case will be, what will be? Output will be 0. So let us see what will be the output. So in this case, output will be 0. When both inputs are low, then output will be 0. When 0 and 1, these two inputs are given, then still output will be 0, because 0 and 1, 0 dot 1 in logical operation will become 0. Similarly, 1 dot 0 output will be 0. But when all inputs are high, that is here, the all inputs are high, then output in that case will be 1. So therefore, the conclusion with the help of truth table is, if all inputs are high, then output in that case will be 1. Right? So all inputs are high, then output will be 1. But if any one of the input is low, then output will be 0. Right? So therefore, with the help of truth table also, you can easily verify that 0 input and 0 input are given, then output in that case will be 0. And for 0, 1, 1, 0, all these combinations, the output will be always low, that is 0. But when both inputs are high, then the output will be high also. So this is what the AND operation and its basic concepts, its truth table, right? Let us consider an example. The voltage waveforms are applied at the inputs of two input AND gate. So there is an AND gate, it has two inputs A and B, and some voltage waveforms are applied at the inputs. Voltage waveforms will be in the obviously digital format. So let us see the voltage waveforms. What are those? At signal at point A or at input A, the signal which is given is like this. It has 0 and 1 inputs, it has 0 and 1 low and highs. And at B, the signal will be like this. So these two digital signals are given to two input AND gates. Now we want to find what will be the waveform at the output, that is at Y, what will be the waveform. So waveform at the output will obviously depend on the inputs which are given, right? So to get the output for respective inputs, we need to know the truth table, right? So for getting the truth table, first of all, let us see what will be the inputs during the time, right? So in this case, on this x-axis, the marking about the time has been plotted. Similarly, here also on x-axis, the marking will be with respect to time, right? So therefore, during 0 to 1, that is during time 0, 1, the inputs are like this. During 1 to 2, the inputs are like this. During 2 to 3, inputs are like this. And in this way, during 6 and 7 also, the inputs are like this. We want to find the waveform. What will be the waveform at the output? The stages in the waveform will be either 0 or 1. There won't be any other stages, obviously. So therefore, to get those stages, we need to use the truth table, right? So the output stages will be 0 and 1, and the truth table I have shown to you. You can see in the truth table, when A and B, that is these two inputs, are 0, 0, then output will be 0, right? So therefore, let us see what is happening during 0 to 1 time period. Okay, let us consider that the time is in seconds or milliseconds. So during 0 and 1 millisecond, what are the stages or states that are represented by two inputs? You can see easily here, during 0 and 1, input at A is 1 and input at B is 0, right? And this is happening during entire this time period of 0 to 1, right? That means you are now talking about the combination this, right? 1, 0. Input A is 1, input B is 0. Then for this combination, the output is, you can see, 0. So at the output side, at the output terminal, the waveform must stay 0 for this entire duration. So therefore, the line that I have drawn is maintaining 0 level for this entire duration between 0 and 1. Okay. Similarly, let us see second one. In the second time duration, that is from 1 to 2, the input signal at A is 0, at B is 0, and you can easily see that this is representing 0, 0, and output should be 0. So therefore, the output waveform during this time period will be 0. Then let us concentrate for third one, 2 to 3. For 2 to 3, for the time period between 2 to 3, you can see the signal at A is 1. Signal at B is also 1. That means you are talking about the combination this, right? So this combination is 1, 1. That is, inputs are 1. Both inputs are 1. Then output, you can see, output is high. So therefore, now for this time period, the output must be high. So this is 1. The stage of 1 must be maintained. So therefore, here the output signal for this time period suddenly increases from 0 to 1. Right? Then, now let us see what will happen in the next time period. For next time period, that is between 3 to 4, the signal at A is 0. Signal at B is also 0. So therefore, 0 and 0, the output signal must be 0. So therefore, this stage must be maintained. So therefore, the line will follow like this. Then next, 4 to 5. For 4 to 5, signal at A is 0. Signal at B is 1. Although it is 1, but still 0 and 1. That is, we are talking about this combination, 0 and 1. So output is 0. So therefore, this line will be maintained as it is. Then for 5 to 6, for 5 to 6, signal at A is 1, signal at B is 0. So therefore, 1 and 0 output will be 0. So therefore, this will be the waveform. And for last one, the signal at A is 1, and signal at B is also 1. So therefore, now you can see the final combination 1 comma 1 and output is 1. So therefore, this stage will be followed as it is, and therefore for 6 to 7 the output waveform will be 1. Therefore, the line will be drawn like this. And this is the last waveform that we need to exhibit. So therefore, the output waveform that I have represented by yellow color is the final output, right? So in this way, waveform can be drawn, right? So the waveform that is now visible to you, right? That is output waveform, which gives you information how a given output waveform can be drawn with the help of inputs present at A and B. Okay. Now let us concentrate to next operation, that is OR operation. So OR operation will be represented by OR logic gate. The symbol of OR logic gate is like this. Again, it will have n number of inputs and one output. The logic gate symbol is something like that. Now this standard symbol has n number of inputs as A, B, C, D up to n, and one single output as a Y output. Since it is an OR operation, so therefore its Boolean equation will look like this: A or B or C or dot 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 up to n. So therefore, the output at Y will depend on the inputs which are present at A, B, C, D dot dot dot, and those will be represented mathematically, symbolically like this. So here you can see that OR word is replaced by plus signs. So therefore, the output will be calculated as A plus B plus C plus dot 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 up to n. But here the plus sign does not represent the algebraic plus sign, but it is a logical addition that will be followed. So therefore, A plus B plus C is nothing but logical addition of the inputs. So if we consider the truth table for two input OR gate, then the true input OR gate will have four combinations, right? 0 0 0 1 1 0 and 1 1. And how to remember these combinations? Again, just a small trick. For A input, you can see 0 0 1 1, and for B input there will be alternate zeros 1 0 1. So therefore, with the help of this terminology, you can easily create four unique combinations: 0 0 0 1 1 0 and 1 1. Now the output will be Y, right? Output will be Y is equal to A plus B, and the output Y is equal to A plus B will be, for 0 and 0, the output will be 0. For 0 and 1, right, 0 or 1, sorry, 0 or 1, the output will be 1. For 1 or 0, output will be 1. And for 1 or 1, output will be 1. So in this way, the truth table will be completed. If you observe the truth table carefully, you can easily find this conclusion, right? If one input is high, the output is high, right? If any one input is high, right? Here you can see these three combinations. In the last three combinations, 0 1 1 0 and 1 1, at least one input is high. So if at least one input is high, then at the output terminal you are going to get 1, right? So output will be high only if at least one input must be high. But if you consider output 0, that is, I am talking about this combination, right? If you consider this combination, you will realize that all inputs must be low, then only the output will be low, right? So this terminology gives you the additional information. If all inputs are low of a OR gate, then output will be 0. Otherwise, even if one single input is high, output will be high, right? So now let us take example as we had discussed in the previous example. There will be two waveforms applied at the two input OR gate. The same waveform that we have seen in the previous case. This will be the signal at A. This will be signal at B. And we are supposed to find the signal, what will be the signal present at output terminal, that is Y terminal, right? So we want to find what will be present at y, right? So therefore, to get this information, right, what will be the waveform at y? First of all, always remember that our waveform will be obviously have 0 or 1 as the signal, no intermediate signal, because we are dealing with digital signal. So therefore, we have divided the given signals into number of time periods, n number of time periods. Here we have divided into 7 time periods. So 0 to 1, 1 to 2, like that. And the digital signals that will be present obviously will be either 1 or 0 at the output. And this is the truth table that is shown to you. Now, with the help of the truth table that we derived in the previous lecture, now let us see what will be the output waveform between the two specific time periods, right? So for this case, let us concentrate for the time period first, 0 to 1. For 0 to 1, the input at signal A is 1 and this is 0. Now, let us search for the combination. The combination is 1 plus 0. Why plus? Because we are talking about the OR gate. So OR gate is represented by plus sign. So you can see easily 1 plus 0. That is, I am talking about this combination. 1 plus 0. Output is obviously 1. So therefore, during this time period, the signal must be high. Right? Then let us concentrate for next one. Now for 1 to 2, the signal is 0 here. Here also signal is 0. So that means you are talking about the combination 0 plus 0. Now for 0 plus 0, you can refer the truth table. That is first combination. It provides you 0 only. So therefore, here the signal will be this one. So therefore, the signal from high will be passed to low one, right? It will be straight, obviously. Then for next 2 to 3, here signal at A 1, here signal at B 1. So therefore, the signal at output will be obviously high, because anyone, if both are high, then output will be high. So therefore, line will be drawn like this. Then for next one, 3 to 4, input at signal is 0. This will be 0. So therefore, this will be 0. So the line drawn will be like this. Then next 4 to 5 may say. So for 4 to 5, this is 0. This is 1, and 0 and 1, the combination provides you high. So therefore, this will be high. So the line drawn will be like this. Then 4, 5 and 6, for time period between 5 and 6, this is 1, this is 0. So 1 or 0, output will be 1. So therefore, the line will be drawn like this, right? I am talking about this combination 1, 0, 1. And last one, this is 1, this is 1. So therefore, 1, 1 output will be high. So this will be the output line. So in this way, the waveform that is given to you in the yellow color will be the waveform present at the output Y, right? So this is what we want to find. Now let us consider the NOT operation. The NOT operation is nothing but NOT gate representation. It's a negation. So therefore, its symbol is like this. This is a standard symbol in which one input and one output will be present, right? So A is the input and Y is the output. Then Y is a complement of A. So whatever present at A will be complemented. So its Boolean equation will be Y is equal to not A, which means nothing but A complement, right? It will be represented as bar on A or dash, A dash, right? So this is called as A complement. This is called as logical complement. And this bubble is nothing but representation of inversion. So whenever in a circuit, when this small circle is represented, then you need to remember that there has to be inversion, there has to be a NOT operation performed on the numbers coming to that bubble. So its truth table will be, obviously, since we are talking about inversion, so therefore at the output terminal, whatever input, it will be complemented. So in binary numbers, 0 will be complemented as 1 and 1 will be complemented as 0, right? So this is a truth table of NOT operation, very simple truth table. You just have to complement whatever number that is input, that will be complemented at the output. Let us take example, same example for this case now. Now only one input will be present at the NOT gate, because NOT gate accepts one input and it complements it. So let us consider the signal at A is equal to like this. And we are supposed to find the output waveform at Y. So let us divide the given signal into number of time intervals. Now with this time interval, we already know that the output waveform will be obviously having two levels, 0 or 1, right? And its truth table is 0 will be complemented as 1 and 1 will be complemented as 0. So let us see what will the output. For first time period, the signal at A is 1, right? So therefore, the output waveform will be complemented, right? If 1 is the input, the output will be 0. So therefore, it will be complemented as this. Then for second time period, 1 to 2, the input is 0, so output will be 1. So the waveform line will be drawn like this. For third case, 2 to 3, the input is high, so the output will be obviously 0 because it will be complemented. So waveform will be like this. Then for next one, 3 to 4, input is 0, so output will be 1, right? Because 0 is complemented as 1, so therefore this will be the line must be drawn for 3 to 4, so suddenly going high. Then for 4 to 5, input is again 0, so the output stays as 1 also. For 5 to 6, the input is 1, so therefore output will be 0, complemented as 0. So therefore stage will come down to 0. Then for 6 to 7, again input is 1, so therefore output is 0. So dear students, this will be the output waveform at Y if the input waveform is given as NOT gates input. So this is how the voltage waveforms can be easily identified with the help of logic and truth table. Now let us go to the universal gates. Now what do you mean by universal gates? The gates which can be used universally. The gates are NAND gate, right, and NOR gate. First we'll see NAND gate operation. Now NAND means not AND. That means it will be complement of AND. So the truth table and all basic symbols will be involving the presence of AND gate, but bubble will be present. You can see in the standard symbol, this will be the n number of input and one output diagram, in which the initial part you can see is representing and one single bubble representing the NOT. So therefore its diagram can be identified as combination of AND gate followed by NOT gate. So therefore output of AND gate will be complemented and given as a Y, which is desired at the NAND gate's output. So its Boolean equation will be Y is equal to not A and B and C, right? Because the output of AND gate is A and B and C and dot 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 up to N, and it will be complemented, that is it will be not. So therefore the Boolean expression is like this. So therefore A dot, B dot, C dot, all those things will be complemented as this in the that is shown in this particular expression. So the truth table for NAND gate will be something like that. You can see here again all possible inputs has been written down, 0011, 0101. So all four possible inputs has been entered for 2 input AND gate. 2 input NAND gate. So for 2 input NAND gate, the output will be A dot B ka complement, that is complement of A dot B. So first we need to find what will be A dot B, and then its output it will be complemented. You can see here in the first case the inputs are 0 and 0. So tell me what will be 0 and 0. 0 and 0 will give you 0, right? 0 and 0 will give you 0. Then its complement, right? Complement of 0 is equal to 1. So therefore output at y when 0 and 0 is 1. For second case, 0, 1. So 0 and 1 will always provide you 0, and it needs to be complemented again, so output will be 1. 1, 0, again same combination. In the case of AND gates, the output of AND gate will be obviously 0, and it will be complemented, right? Whatever the output of A dot B will be complemented, and definitely it will give you 1. But when there is the inputs 1 and 1, right? When there is a inputs 1 and 1, right? So the AND gate's output is 1, but for NAND gate, it needs to be complemented. So therefore, after complementing it, 1 will be complemented as 0. So therefore, output for last input is 0. So therefore, this is the NAND gate operation and its truth table. Remember, this NAND gate is nothing but not AND. So first AND gate, and then it will be followed by its complement, that is NOT gate. Now let us see NOR gate in operation. So for NOR gate operation, again NOR, that is not OR. So it's a combination of two gates, NOT gate and OR gate. So therefore its symbol is, it's initially the symbol of OR gate, and it will be complemented as you can see in the diagram, right? First initial part representing OR gate and the bubble representing the NOT gate. Again, it is N input. So therefore, n number of 2 or more inputs can be connected to OR gate, but output, at the output, you will get only one output. It's a combination of OR gate, right, followed by NOT gate, right? So this is the representation of NOR gate. So its Boolean equation or logical operation will be not OR, right? So not, and between A and B and C, there will be or, like that. So therefore, symbolically, it will be complement of A plus B plus C plus, right? And plus sign is nothing but logical addition. It's not actual algebraic addition. So it's truth table for 2 input NAND gate. You can see all possible inputs has been written down, and we are supposed to find what will be present at the output case. Now for output case, you can see for 2 inputs A and B, the output will be A plus B and its complement. So complement of A plus B. So first of all, we will try to find what will be A plus B and then complementing it. So for 0 plus 0, output will be 0 always, right? Because it's a OR gate. So OR gate truth table says that 0 or 0 always 0, and it will be complemented. So therefore output will be 1. So therefore at output of 0 and 0, it will be 1. Now for 0, 1, so it will be 0 plus 1, and 0 plus 1 becomes 1 in OR gate, right? And that OR gate will output will be complemented. So complement of 1 becomes 0, so therefore output will be always 0. Then 1 or 0, right? So 1 plus 0, output will be 1, and it will be complemented, so the output will be 0. And final one, 1 plus 1. Now for 1 plus 1, it is not 2, dear students, it is 1. Because it is not plus, it is a logical OR operation. So 1 or 1, output will be 1, and it will be complemented, so the output will be 0. So for NOR gates operation, you will realize that all inputs are low, then output is high, right? Now let us concentrate to special gates. The special gates are 2, XOR and XNOR. First of all, what is XOR operation? XOR, or it is also called as exclusive OR operation. This is a standard symbol for exclusive OR operation. You'll realize that it's a OR, but behind that OR, there is another curved line drawn. It has n number of inputs and one single output. So therefore, Boolean equation for 2 inputs, that is A and B. Let us see what will be that. Y is equal to X XOR B, A XOR B, right? Symbol of XOR mathematical symbol or is, you can see this will be the symbol. A plus, it's not exactly plus, but it is called as A XOR B, right? This is XOR operation symbol, but it is equivalent to A dot B bar plus A bar dot B. That we will see in the next chapter, but right now just remember XOR operation is equivalent to A dot B bar plus A bar dot B, right? So therefore, let us see how to get the truth table for this case also. So for 2 input XOR gate, the truth table will be like this: 0 0 0 1 1 0 and 1 1 combinations, and output will be Y is equal to A XOR B. Now let us see how to get the output in this case. Here you can see the inputs are 0 and 0. So instead of A, I am going to put 0 dot. Instead of B, it will be 0, and that is 0 complement of 0, right? Plus A is again 0, but its complement dot B, right? So 0 dot, what will be complement of 0? It will be 1. So therefore 0 dot 1 plus 1 dot 0. Now you'll realize that 0 dot 1 is 0 and 1 dot 0 is also 0 and 0. So you'll get 0 plus 0, right? Sorry, 0 plus 0. And now you know that what will be 0 plus 0, and 0 plus 0 output will be 0. Then next combination 0 1. So XOR of 0 1. So 0, A is 0 dot 1 is B and its complement plus A is 0 complement dot B is 1. So let us see what will be the output of this. 0 dot complement of 1 is 0, so 0 dot 0 plus 0 complement is 1 plus dot 1. So you'll realize that 0 dot 0 is 0, 1 dot 1 is 1, so you'll get 0 plus 1, that is 0 or 1, and 0 or 1 output is 1. Then 1 0 combination, so that is A is equal to 1 and B is equal to 0 combination. So A is equal to 1, so complement of 1 dot B is equal to 0. So you'll get 1 dot, right? Complement of 0 is 1 plus complement of 1 is 0 dot 0. You realize that it is 1 plus 0, right? 1 dot 1 is 1 and 0 dot 0 is 0. So therefore 1 plus 0 output is 1. Then final combination 1 and 1. So therefore A is 1 dot B is 1 and its complement plus A is 1 complement plus B is 1. So output will be 1 dot, what will be complement of 1? It will be 0 plus complement of 1 is 0, so 0 dot 1. Here you realize that 1 dot 0 is 0 plus 0 dot 1 is 0, so 0 plus 0, that is 0 or 0, answer is 0. So this will be the output for exclusive OR operation. How to remember? You can easily remember output of exclusive OR operation 0 1 1 0, right? 0 1 1 0. Now exclusive NOR operation, now difference between the two is the bubble that will be present somewhere here, right? It's same as XOR, but the bubble will be present at the output, right? This bubble represent the NOR operation, right? Not OR. So this is exclusive NOR operation. It has n inputs and one output. So its Boolean equation for two inputs, that is A and B, will be A XNOR B. And its symbol representation is complement of A XOR B. So XNOR means complement of XOR. So therefore at the output terminal you can see the equivalent representation of this is A dot B bar plus A bar dot B and its complement, right? This complement. Why? Because this is the complement. So its truth table for 2 input XOR gate can be calculated with the help of the output that you have already got for the XOR gate, right? It should be not XOR, it should be, sorry, XNOR, right? It should be XNOR. Okay, so the truth table for 2 input XOR gate, right? So you already remember, I already told you the output truth table can be easily remembered as, for XOR it is 0, 1, 1, 0, right? So the XNOR will have output complement, right? 0, iska complement, iska complement, and iska complement. So the complement of 0 is 1, here it will be 0, here it will be 0, and here it will be 1, right? So therefore the output for XNOR gate will be 1, 0, 0, 1. In this way you can remember that output of XNOR gate. So all these gates and their symbols and their truth tables has been identified in this video, right? So in this video we have seen AND gate, OR gate, and NOT gate symbol and truth table. These are the basic gates. Then universal gates, why they are universal we will see in the next video. The universal gates are NAND gate and NOR gate, and 2 special gates, that is XOR gates and XNOR gates, and their truth tables also. So with the help of this information we can easily now find how this universal gates are called as universal gate, but that we'll see in the next lecture.